onto n dash. N to n dash. Then T is 1 1 mapping, means 1 to 1 function, meaning, and T dash as a bounded if and only if there is a positive real number, m such that m of norm of x of norm of x m of norm of x less than or equal to norm of t of x for all x belongs to n. Equation this consider equation number 1. This consider equation number 1. So once again I will do the statement 3.4.2 theorem statement that n dash be normal linear space and let T be a linear transformation of n to n onto n dash. Then T is 1 1 and T dash as bounded if and only if there is a positive real number m such that m norm of x less than or equal to norm of t of x for all x belongs to n. This you consider 1. Proof. No, now we will discuss proof. So here proof. Let us assume that 1 holds good. 1 holds good. We need to prove that T is 1 1. Need to prove that T is 1 1, comma T inverse is bounded for let x1 comma x2 belongs to n such that T of x1 equal to T of x2. So therefore T is a linear. This can be written as T of x minus within the bracket x1 minus x2 equal to 0. Then we have positive real number. We have positive real number m such that m of norm of x1 minus x2 norm less than or equal to norm T of x1 minus x2 norm T of x1 minus x2 equal to 0. So from this it follows that norm of x1 minus x2 equal to 0. That implies x1 equal to x2. So x1 equal to x2 means that is 1 1 function. What is 1 1 function? Distinct elements capital A have the distinct images in capital B. So f of x1 equal to f of x2. x1 equal to x2. We'll say that function is 1 1 function or injective function. So T is linear. T of x1 minus x2 equal to 0. We have a positive real number m such that m of norm of x1 minus x2 less than or equal to T of x1 minus x2 that equal to 0. From this it follows that norm of x1 minus x2 equal to 0. That implies x1 minus x2. Thus T is 1 1 function or injective mapping. Since T is onto for each y belongs to n dash, there exists x does not belongs to n such that T of x equal to y. That implies T inverse y equal to x. Hence the inequality 1 gives m of norm of T inverse y is less than or equal to norm of y for all y in n dash. That is norm of T inverse y less than or equal to m norm of y for all y in n dash, where m equal to 1 by m. That implies T inverse is bounded. Here T inverse is bounded. Conversely, let T inverse be bounded and T be 1 1 function. To prove that T satisfies equation number 1, let x be an arbitrary element of n. So let y equal to T of x equal to n dash. Since T inverse is bounded on n dash. In this theorem, what we proved first, this is a 1 1 function and onto function. That T inverse is bounded. T inverse is bounded. T inverse is bounded n dash. There exists a positive. There exists a positive number m such that norm of T inverse y, the norm less than or equal to m of y for all y in n dash, for all y in n dash. So norm of x equal to norm of T inverse y less than or equal to m, norm of y equal to m, norm of T of x. It follows that 1 by m, norm of x less than or equal to norm of T of y for all x in n from 1 small m equal to 1 by capital M. This completes the proof of the theorem. So unit 3, bounded linear transformation based upon concepts. One theorem we proved. What are the concepts? The L and L dash be two linear spaces over the same scalar field F. The mapping T L to L dash is called linear transformation. Satisfies the following axioms. So T of x plus y equal to T of x plus T of y for all x belongs to x comma y belongs to L. P of alpha x equal to alpha into T of x. P of alpha x plus beta y that equal to alpha of T of x plus beta of T of y. For T of 0 equal to 0 and T of minus x equal to minus T of x for all x belongs to L. We are using these concepts or these properties, linear space properties. We proved 3.4.2 theorem, most important. So what in this theorem, what we proved first? We proved T is 1 function and onto function. If it is function is 1 and onto exists, inverse also exists. And next we proved bounded. Bounded, but conversely, let T inverse be a bounded and T is 1 function. To prove that satisfies equation 1. Let x be an arbitrary element of n. Let y equal to T of x equal to n dash. Since T inverse is bounded on n dash, there exists a positive number m such that norm of T inverse y less than or equal to m of y for all y in n dash. Norm of x equal to norm of T inverse y norm less than or equal to m, norm of y that equal to m, norm of T of x. It follows that 1 by m norm of x less than or equal to norm of T of y for all x in n from 1 m equal to 1 by m. This completes the proof. If you have to learn this theorem, most important 3 point exam point of the 3.4.2. So another one short answer question we'll discuss based upon this chapter rules. What are the show that the following mappings from R2 into R square in linear transformations. What are the question? First one is short answer question 1. Short answer question 1. T of x1 comma x2 that equal to x comma 0. The given x comma 0. Next, T of x1 comma x2 equal to alpha x1 comma alpha x2. Alpha is a field real number. Third one, T of x1 comma x2 that equal to x1 comma x2. Here short answer question most important based upon properties only. So based upon show that the following mappings. So that the following mappings. So that the following mappings R square into R square are a linear transformation. First one, T of x1 comma x2 equal to x comma 0. So second property is T of x1 comma x2 equal to alpha x1 comma alpha x2. Alpha is a scalar. So third property, T of x1 comma x2 equal to x1 comma x2. So solution, let x equal to x1 comma x2. No nice place. So T of x1 comma x2 that equal to x1 comma x2. Let x equal to x1 comma x2. Y equal to y1 comma y2. and x belongs to R, set of real numbers. Then first one. What is first one? T of x plus y can be written as, in place of x, we need to substitute what we took, let x equal to x1 comma x2. No? In place of x, we are substituting x1 comma x2. In place of y, we need to substitute y1 comma y2. That implies, that can be written as T of x1 plus y1 comma x2 plus y2. What we did here, T of x plus y, we wrote T of x1 comma x2 plus y1 comma y2. That equal to, here we joined x1 y1. Here we joined x1 y1 one place and x2 y2 another place. So T of x1 plus y1 comma x2 plus y2. That is nothing but T of x. Here x1, that is nothing but x plus y. T of x plus y by definition. So that implies, so T of second property, that equal to x1 comma 0, because they given in the question, short answer question one, first one, you have to observe T of x1 comma x2 is given x comma 0. Second property, what is given? T of x1 comma x2 equal to alpha x1, alpha x2. So alpha is a field, a real number. Third property, what is given? T of x1 comma x2 equal to x1, x2. The similar way here, x1 comma, in place of y1 we wrote 0 plus y1 comma x1 comma 0 and y1 comma 0 by given condition, first condition. So that can be written as T of x plus T of y by definition of addition in R2. Okay, today the given definition. So finally, what we proved? First condition, T of x plus y. Here we proved T of x plus T of y using this the given condition. So second one, what is second one? T of alpha x equal to T of alpha x1 comma x2. T of alpha x1 comma x2. That equal to T of alpha x1 comma alpha x2. T of alpha x1 x2. The given condition. That equal to alpha comma 0 by definition. Alpha comma 0 by that equal to alpha of x comma 0. That equal to alpha is outside T of x, because T of x1 x2 equal to x comma 0. That equal to T of x. So what we proved here, second condition, T of alpha x, we proved alpha into T of x. So second property, second one. So first T of x plus y, T of x plus y. This can be written as T of x1 comma x2. X1 comma x2. X1 comma x2, y1 comma y2. So in place of x, what we did here, in place of x, x1 comma x2. In place of y, y1 comma y2 substituted. T of x1 comma x2 plus y1 comma y2. That implies T of x1 plus y1 comma x2 plus y2. That equal to alpha x1 plus y1 plus alpha x2 plus y2 by definition. That equal to a into here, that equal to alpha into x1. So alpha we are taking inside, because here you are multiplying alpha into x1 y1, alpha x1 plus alpha y1 comma alpha x2 plus alpha y2. Then what we did, again join the like terms. Like terms means here alpha of x1 plus alpha x2 comma alpha of y1 plus alpha y2. So by definition, so here we need to take alpha as common. You are taking alpha as common, what we get? X1 plus x2 comma alpha we took common means y1 plus y2. So then here alpha x1 here second condition what is given in the question. So that the following mappings are r square into r square are linear transformations. The second property the given t of x1 comma x2 that equal to alpha x1 comma alpha x2 alpha x1 comma alpha x2 alpha field field. Here second property t of x1 comma x2 equal to alpha x1 comma alpha x2. So here here what they use alpha into x1 plus x2 that is nothing but that is nothing but x. Here alpha y1 plus y2 nothing but y that equal to t of x plus t of y, t of x plus t of y by given condition. Next, second condition. So t of lambda x, t of lambda x that equal to t of lambda x1 comma x2. Yeah, lambda is a scalar here, nothing but it is a real number. So t of lambda x1 comma x2 equal to t of lambda x1 comma lambda x2 that equal to lambda x1 lambda x2. So in these two condition, this condition we took lambda outside x1 comma x2 that equal to lambda x lambda x. Thus t is a linear transformation on r square into itself into itself. Once again this one what we took t of lambda x t of lambda x that equal to t of lambda x1 x2 that equal to t of lambda x1 comma lambda x2 lambda x1 comma lambda x2 that equal to lambda x1 comma lambda x2 that equal to lambda x1 comma x2 that equal to lambda of t of x. Lambda is outside complete like alpha t of x. Thus t is a linear transformation r square into itself into itself. Then third problem, third condition. What they given third condition? T of x1 comma x2 equal to x1 comma x1 x1 comma x2 x1 comma x2. Right here third one, third property. T of x plus y t of x plus y t t of x1 comma x2 plus y1 comma y2. What we did here using third property, third condition, using third condition, in place of x we substituted x1 comma x2 plus y in place of y1 comma y2 that equal to t of x1. This we are shuffling means joining the like terms. Like terms means x1 plus y1. No nice place. Here x1 comma x2 plus y1 comma y2 equal to here joining the like terms means x1 plus y1 we note one place comma x2 plus y2 another place by definition. Here that means x1 comma x2 plus y1 comma y2. This is nothing but t of x plus t of y by definition. You are using third property. So next second one, t of alpha x. Thus t of alpha x1 comma x2 that equal to t of alpha x1 comma alpha x2 by definition that equal to alpha x1 comma alpha x2 that equal to alpha x1 comma x2. So x1 comma x2 is nothing but x. Here first only we took let x. So that equal to alpha of t of x. Thus t is linear transformation r square into itself. So we proved one here one concept, properties, one theorem, and one short answer questions. Once again, we'll revise what we discussed today. Unit 3, bounded linear transformations. Right. So concepts. Concept. Concepts. So L and L dash be two linear spaces over the same field scalar field F. The mapping T L into L dash is called linear transformation. Satisfies the following axioms. What are the axioms? T of x plus y that equal to T of x plus T of y for all x comma y belongs to L. A second one, T of alpha x that equal to alpha T of x. A third one, T alpha x plus beta y. First and second concepts we are using third property. So alpha into T of x plus beta into T of y. So fourth one, T of 0 equal to 0. T of minus x equal to minus T of x for all x belongs to L. So most important theorem, what is that? 3.4.2 theorem. What is that statement? Let n and n dash be normal linear space and let T be a linear transformation of n onto n dash. Then T is 1, 1 and T dash is bounded. If and only if there is a positive real number m such that m of norm of x less than or equal to norm of T of x for all x belongs to n. This we consider one equation number 1. So proof once again. Let us assume that 1 holds good. We need to prove that T is 1, 1. T inverse is bounded. So T is 1, 1. Means for let x1 comma x2 belongs to n such that T of x1 equal to x2. T is linear. Here x1 minus x2 equal to 0. Then we have positive real number m such that m norm of x1 minus x2 less than or equal to thus T is 1, 1. So T is onto for this purpose y belongs to n dash. Y belongs to n dash. Their existence x does not belong to n such that T of x equal to y that a plus T inverse y of x equal to x. Hence the inequality 1 gives m of T inverse y less than or equal to norm of less than or equal to norm y for all y in n dash. That is norm T inverse less than m norm y for all y into n dash when m equal to 1 by m. The T plus T inverse is bounded. Conversely also we are proving that T inverse be bounded and T is 1, 1 function. To prove that T satisfies 1, let x be an arbitrary element of m. Let y equal to T of x equal to n dash. Since T inverse is bounded on n dash, there exists a positive number m such that norm of T inverse y less than or equal to m of y for all y in n dash. Norm of x equal to norm of T inverse y less than or equal to m norm y that equal to m norm of T of x. It follows that 1 by m norm of x less than or equal to norm of T of y x in n dash from 1 m equal to 1 by m. This completes the proof of the theorem. So in this theorem, what is the important bounded linear transformations? Concept based upon concept, one theorem and one short answer question we discussed today. So we'll meet on next Saturday. Thank you.